Hello, this is the final presentation by Team 5 for the class ME 452. We will be going over the analysis and redesign of a valve. Our team is made up of Nicole Basil, Hannah Ho, Layla Muhammad, Zoe Nathanson, and Karen Nee. The valve is a device that controls the flow of water in a piping system by changing the area of the flow, ranging from completely open to completely closed. It is very common. The valve we have chosen is depicted by the images of the CAD model shown here. This in particular has a hand wheel, which means the flow of water can be changed more finely. We have depicted the expanded view of the valve as well.
Our primary customer for the gate valve would be wastewater management companies, which use a multitude of valves in creating pipe networks, including gate valves, and they would rely on the functionality of these valves to manage wastewater in a city. There would be component variants for pipe networks of a community, as opposed to our secondary customer of plumbing companies, which would replace components of a building's water system, such as using gate valves. They would also rely on the functionality of these valves to make reliable fixes to keep their customers satisfied, and they would use component variants for pipe networks of a building instead of a community.
We did a functional analysis for the redesign of a valve, and the main purpose of a valve is to control fluid. And then as you move right, you can see we had 7 final functives that we came up with.
The function component mapping matrix is used to match the components of the gate valve to their respective functions. As you can see here, most of these components are used to withstand pressure and prevent leaks. The spindle, bridge, handwheel, and bracket are used to switch positions, while the body is the main part that contains the fluid. On the next slide here, the gate or plunger is used to create and block the passage.
We also did a bill of materials. As you can see off to the right, we have a key corresponding to the quad chart classifications, and those colors show up in the bill of materials. Our final price came out to be just over $650.
Here we have the functional differential table and the component commonality table. We see the functions that are the same between the two customer groups. For the differences, we have how we show status and how much pressure needs to be contained. For the component commonality table, the components that need to be modular are the hand wheel and the gate. Everything else can be the same between the two customer groups.
Using the differentiation table, we were able to design modifications for the secondary customer's design variant to make the valve more suitable for their use. The handle design was modified from the more precisely controlled wheel to be an on and off handle for the secondary customer. This is sufficient for the plumbing needs for stopping the water flow during repairs and replacements. The plunger design was modified to a rubber stop for ease of quickly blocking and opening the flow of the water when the handle is turned. This view shows the common interfaces between the modules and the platform. The spindle is a common interface for the handles. The primary variant handle is press-fitted onto the spindle, whereas the secondary variant uses a set screw to connect to the spindle. The common interfaces for the plunger variants are the spindle and the bushing. Both variants are rigidly attached to the spindle. The variants interact with the bushings by being spun into and out of it, controlling the water flow.
These are the 2 primary feasible assembly sequences for the valve. Assembly sequence 1 contains 2 subassemblies, whereas assembly sequence 2 only contains 1 subassembly. Assembly sequence 1 contains a subassembly containing the hemisphere, gate, and bushing. However, because these are only loosely joined with each other and not fastened with each other, this makes it more difficult to transfer or handle the subassembly, and it also makes it more difficult to test it. Therefore, assembly sequence 2 was chosen as our primary assembly sequence. Using our chosen primary assembly sequence, we indicate the differences between the primary variant and the secondary variant, with the differences being either a metal gate or a rubber gate being used, and a hand wheel or a flat handle being used. We created a modified product family assembly diagram based off of the primary assembly sequence indicated by our fishbone diagram. The original product family assembly diagram has product differentiation early on in the assembly, whereas if the subassembly indicated in the fishbone diagrams were to be built first, then this would allow for product differentiation much later on in the assembly of the valve.
Now we'll talk a little bit about designing for manual assembly. Here is our initial analysis. You can see our efficiency is only about 20% efficient. We decided to redesign the cover, which is a platform part, and the hand wheel, which is the module part. The cover has many fasteners and it's relatively expensive, so we thought this would be a good candidate. And the hand wheel has complex geometry and is also relatively expensive. For the cover, we have some pictures here of the before and after the redesign. The timing actually increased after the redesign. However, the cost drastically decreased, as can be seen in both of the tables. Regarding the redesign of the hand wheel, we can see the pictures of before and after again. The timing here was the same for manual assembly, however the cost also drastically decreased here. Regarding the final analysis of designing for manual assembly, we can see that we increased the efficiency by 11% to make it 31% efficient. The snap fit of the cover removes the need for previously used medium studs and large hex nuts, which saves lots of time and lots of money.
In the initial analysis for the automated assembly, we can see there are 11 different parts with a total assembly cost of just over 48 cents. The redesigned part combines the V-filler, gland, and bridge into one part, reducing the number of parts in the assembly and using one type of fastener. This complies with the design for automated assembly guidelines such as reducing the part count, reducing the fasteners, reducing part variety, increasing part symmetry, and adding features for easy insertion. After the redesign, we were able to reduce the assembly to 7 different parts and the total assembly cost to just over 44 cents. When considering the performance, this redesign will maintain the ability to withstand pressure and prevent leaks. The manufacturing cost would decrease since there is this one symmetrical part instead of 3 parts to be manufactured. It will also maintain the support stability for the valve. For process selection, we analyzed the cover and the hand wheel. The critical dimension of the cover is the height of the undercut to ensure it is able to secure properly with a tolerance of plus or minus 0.1 millimeters. The hand wheel has a tolerance of plus or minus 0.5 millimeters, and the rib thickness is the most critical dimension. With taking these tolerances along with the other 7 process capabilities into consideration, we determined the sheet metal working is the best for the cover and injection molding is the best for the hand wheel because they are capable of achieving the batch size.
For design for manufacturing for the cover redesign, we performed the cost estimation using the analytical method in the design for manual assembly slide. Here we included an isometric view of the CAD after the redesign with the key dimensions for the selected primary process of sheet metalworking. The main differences in the before and after design are seen in this table. DfM Pro was not used due to the original piece being die-casted rather than sheet metal worked. Here we included a CAD drawing of the cover redesign with all the dimensions, and we also included the isometric view in the corner. In order to estimate the cost savings for our cover redesign, we compared both the analytical method of cost estimation and using hubs. And we were unable to use hubs for the before design because the design of the cover was die-casted and hubs is only used to create a quote for machining and sheet metalworking. The hubs calculation for the after design can be seen on the left, and as you can see, both the analytical method and hubs method for cost estimations are lower for the after design than the before design. For design for manufacturing for the hand wheel redesign, similar to the cover, the cost estimation for the analytical method was done in the design for manual assembly slide. And here we have an isometric view of the CAD after redesign with key dimensions for the selected primary process of injection molding. We also included a table below including the differences of the before design versus after design. And again, DfM Pro was not used due to the original piece being die-casted rather than injection molding for this redesign. We also included a CAD drawing with all the dimensions of the hand wheel and the isometric view in the corner for reference.
For our product service system, we are introducing free lifetime consultation and replacement parts available for purchase at their base manufacturing cost. For customers, this will ensure that the product is being used for its intended purpose and that it is the best option available for their needs. It will also incentivize them to purchase replacement parts if they are offered at their manufactured cost. And it will also reduce maintenance costs overall by allowing the option of replacing parts instead of replacing the entire product. For the environment, using the product for its intended purpose can reduce misuse and potential water leaks because these valves are being used for water systems. And the parts of the product that are no longer being used can be recycled instead of trashing the entire product. In conclusion, our redesign reduced the cost in both the automated and manual assemblies by overall of $64. Increased assembly efficiency of the manual assembly from 20% to 31%, and it also allowed for more delayed differentiation in the product family, and the established product service system improves customer experience and sustainability. We reduced the amount of fasteners by replacing the studs and hex nuts with snap fit design. We consolidated the subassembly to reduce the total number of parts from 33 to 19 parts. However, due to the large parts, the redesign mostly benefited the manual assembly instead of the automated assembly, and most of the parts have a complex geometry that results in a lower orienting efficiency. In the future, we would create smaller and simpler geometries for the subassembly to increase the efficiency for the automated assembly.